Hello everyone, welcome back to the latest session. In the last session, we were looking at the different oxidizing agents that are used as disinfecting agents. And in that context, we looked at HOCl and OCl minus and the relevant acid-base chemistry and equilibrium. Why? Because HOCl is a much stronger oxidizing agent compared to OCl minus, and their ratio, it's like a balance, right? If the total OCl minus is this, depending on the pH, it's going to either tip this way, more HOCl and less OCl minus, or if I increase the pH, it's going to tip this way. So, what we wanted to illustrate in the last session was that pH will play a role in deciding this equilibrium between the acid and its conjugate base, and obviously pKa, the acid dissociation constant, will come into picture. So, let's move on and look at what else we were discussing. Then we started looking at disinfection byproducts. For example, I am adding my oxidizing agent Cl2. As long as it reacts with my pathogens, this is fine. I want this to happen. But it's not just pathogens that are present in the solution. You will still have some organic matter, right? And this organic matter can be the organic matter left from my treatment activated sludge process. After activated sludge process, some of the microbes can come out, which are not pathogens, or some of the substrate can come out, because you can't really achieve 100% efficiency. You are always going to have BOD of 10, 20 or even 30 depending upon the type of process you are using. So, you always will have some organic content. In water, natural waters, river waters, you will have what is referred to as natural organic matter. Why do we say natural? Because the sources are from natural sources, leaves, dead aquatic plants and such, let's say dead aquatic life. So, when they die again, they are going to leach into the water and you are going to have natural organic matter. So, but if chlorine or this oxidizing agent reacts with organic matter, I will have what are called as disinfection byproducts. This I do not want to form. So, the case is clear. I want to choose that oxidizing agent depending upon its ability to effectively inactivate the pathogen at hand while not forming a lot of or relatively limited disinfection byproducts. So, that is the key. Another aspect to limit formation of disinfection byproducts is to see to it that the organics concentration is less, so that even if I add the chlorine, then disinfection byproducts are not going to be formed. Let us dig further. So, formation, we already looked at this. The key aspects are, we want an oxidizing agent which is usually chlorine, and we need a electron donor. This is an electron acceptor, and obviously for the redox reaction here, the electron donor is the organic matter. Let's see. Let's move on. So, typical natural organic matter structure. As you can see, it's not a simple, what do we say, compound, and there is no one structure. You have, it's pretty long chain, you have a lot of aromaticity. So, it's a complex molecule, obviously life, right? So, you have humic acid, fulvic acids and such. So, they are all part of this natural organic matter. So, what we want to illustrate is that it's a pretty complex molecule. Let's say, again, this is only a typical representation. So, what happens when we add Cl2, right? So, when we add Cl2, it can lead to oxidation, and the byproduct of that case will be Cl minus. Okay, that's fine. Or it can lead to substitution to form chlorinated organics, which are called the disinfection byproducts. Let's see. Right. So, this is fine, it is not toxic to us at those levels, but when we have substitution to form chlorinated organics, that is when we are going to have issues. So, how will it work? So, I have HOCl or Cl2 and I have these aromatic rings. I am going to have substitution, let us say 1 Cl, 2 Cl or 3 Cl, let us say, right. And small segments, I guess, can break off, and one common product is CHCl3. Chloroform, let us see, right. So, these kinds of disinfection byproducts are called trihalomethanes. Methane is CH4. So, the different kinds of what do we say, THMs are CH3Cl, CH2Cl2, CHCl3, right, trihalo. So, trihalogen, Cl is a halogen, Cl minus is a halogen, and you have trihalomethanes, let us say, right. So, trihalomethanes, and these are toxic to us. And if there is bromide Br minus present, so it can also lead to kind of formation of disinfection byproducts, but in general when there is bromide, we are typically concerned with its reaction with ozone, let us say. So, we saw earlier that ozone can also sometimes form disinfection byproducts, but that is the case when there is Br minus, that is something to keep in mind, right. So, different kinds of disinfection byproducts, one class is the trihalomethanes, other class is the haloacetic acids, right. We will come back to that. So, in India, let us say, at least based on my limited experience, the dissolved organic matter is a concern. When there is high dissolved organic matter and chlorine comes in contact with it, you are going to have disinfection byproducts which are carcinogenic to humans, depending on the concentration, level of exposure and time of exposure, but they are certainly toxic and a sure way to kill the aquatic life. That is something to keep in mind. So, that is why whenever in India, at least wastewater treatment plants, people try to use chlorine, they do it for two reasons, because their activated sludge process or the biological treatment does not work very well due to poor maintenance or due to poor operation, sludge retention times being very less or soil retention time being less and so on. So, here they use chlorine for two purposes, not just for disinfection. Chlorine is also an oxidizing agent. So, you can oxidize the organics left, so it will be as if BOD is less. But by adding this amount of chlorine, you are forming a hell lot of disinfection byproducts which you are releasing into the water body and killing or affecting aquatic life greatly. So, thus again the enforcement agencies aren't looking at it, but again if you are either an informed citizen or end up being in charge of a plant, hopefully you will look into that. Do not add chlorine to what we say wastewater treatment plant effluents. At least that is based on science too. So, in India though, what is it now? The DOC is very high. I am not calling it dissolved organic matter. Why? In the context of Indian surface water bodies, it is not just the organic matter from the natural sources that is of issue, or I am not calling it NOM, pardon me. I am not calling it natural organic matter, I am calling it dissolved organic carbon or dissolved organic matter, right, because here we have high influence of the humans or anthropogenic sources of organic content are pretty much prevalent, let us say. So, that is why I am not calling it as NOM, and that is the reason why it is pretty high. DOC or DOM levels are very high in India, especially in Yamuna. In general, let us say it is 2 to 3 or 2 milligram per liter in most developed countries. So, when I add chlorine either for water treatment or for wastewater treatment, so at least for water treatment I add chlorine to disinfect the water, I add a lot of chlorine or have to add a lot of chlorine to take care of this high organic matter. So, the disinfection byproducts that are going to be formed are going to be at very high concentrations. That is something to keep in mind, right. So, types of DBPs, so trihalomethanes, we looked at that, and haloacetic acid. Acetic acid is CH3COOH, haloacetic acid. So, here instead of H3 you can have CHClCOOH, right. I think you can even have CHBrCOOH and so on and so forth, let us say different combinations, right, H2 I guess. So, these are called haloacetic acids, but again as we can see for the total organic halogens let us say Cl minus, Br minus, these trihalomethanes and haloacetic acids only cover around, what is it, I guess 40% or 42% of the total organic halogen concentration. There are other unidentified what do we say, organic halogens out there. So, again these wreak havoc with the aquatic ecosystem. You should not try to or you should try to limit this whenever possible. So, we already looked at this, right, CHCl3 chloroform, bromochloromethane, dibromochloromethane, CHBr3 bromoform. Okay, I guess I stand slightly corrected. Earlier I was talking about something like CH2Cl, right, so or Cl2. So, that is not the case. It is trihalo, as you see everywhere it is trihalo or 3 halogens, Cl3, 3Cl or 2Cl, 1 Br minus. Okay, here I guess one of it is missing, Br2, it is dibromo. So, dibromochloromethane or bromoform, let us say, right. So, that is something to keep in mind. That is why I guess it was called trihalo. I stand corrected. So, haloestic acid again mono chloro, 1 chlorine or Cl minus, dichloro, trichloro, mono bromoestic, dibromo. So, you can substitute accordingly in CH3COOH. All these are halogenated organics, right. So, chlorine dosage, now I want to know how much chlorine to add. So, we know that I am adding chlorine as an oxidizing agent, and when I am adding that, I need to take care of both the oxidation of the organics and other reduced forms, and also I need to have enough chlorine to kill my pathogens. So, two aspects, right. I need to take care of organics and other reduced compounds, let us say manganese, iron or such, and then I need to have enough left for my pathogens, right. So, this is a aspect that I need to add. So, when I add chlorine or oxidizing agent, I need to take care of both. So, I need to look at this because I need to ensure adequate residual chlorine or ensure that. So, for that we have something that is called as breakpoint chlorination. We will see how that comes about. Let us see. Before we go further, one aspect to note is that we know from our wastewater relevant aspects that we have ammonia or NH3 in our solution, and if we add an oxidizing agent, we know that it can go to monochloramine, and depending on the concentration of Cl or HOCl, it will go to dichloramine and HCl2, and if I add it at a higher concentration, or finally it can end up into NCl3, which is pretty unstable, and it will end up going to N2, nitrogen gas finally. So, this is some background we looked at. Why did we look at that? We were looking at formation of NH2Cl and NHCl2, which are themselves forms of combined chlorine, which we add as disinfecting agents. But we also need to be aware of this. Why? Because you know that in our wastewaters you can have NH3. So, if I am adding HOCl to kill the pathogens, the HOCl will not just react with the pathogens, it will react with whatever it sees out there, right. It is not so specific, it is an oxidizing agent, it can react with other organic matter, it can react with the ammonia that is present, right. And after all this, then I guess not after, assuming that all of them are taken out, then we will come to providing the residual chlorine or free chlorine, so that pathogens can be taken care of. So, this is the aspect we need to look at. I need to add enough oxidizing agent or chlorine or HOCl to take care of the organic matter, to take care of NH3 before I can take care of the pathogens. So, let us see what we have. So, here we have a good graph from our two pieces of graphs or two graphs from Metcalfe and Eddy. So, what do we have? We have chlorine residual on the y axis, and on the x axis what do we have? I think we are increasing it out here, transformation of ammonia, Cl2 and such, right. Okay. So, let us look at that. So, here what is it now? As I add it, right, from here I am starting to add. So, here what is happening initially, you have destruction of chlorine due to oxidizable substances such as Fe2 plus. Fe2 plus, right, can go to Fe3 plus by giving out its electron, let us see. So, it is an electron donor, and my Cl2 or HOCl or oxidizing agents, they will accept an electron. So, whenever I have Fe2 plus, they will readily consume my oxidizing agent, let us see, right. So, that is why when I have reducing agents such as Fe2 plus or H2S, they will be immediately consumed. So, there is no residual chlorine as I keep adding it, right. Keep adding my oxidizing agent or the chlorine. So, it is everything will be oxidized, or all the oxidizing agent is consumed, and then by here I am done with all the readily oxidizable compounds like Fe2 plus and H2S. So, now as I keep adding more chlorine, what is going to happen now, right. So, here the NH3 that is in the water will start reacting with the HOCl or Cl2 that I am adding, and it will first form monochloramine, and if I increase the concentration, it will form dichloramine. So, that is what you will see here. So, formation of chloroorganic and chloramine and chloramine compounds, let us see. But again, keep in mind, this is chloramine residual. So, even if it is a combined form, that is why we are saying that it is increasing, let us see. So, this is increasing. But if I keep adding more, what's going to happen? If I keep adding more, I know that it's going to be further oxidized to nitrogen trichloride, which is unstable, and it will go to N2, right. So it's leaving the system, let's see, right. So the form of this combined chlorine, it's not now NH2Cl and then NHCl2 is increasing here, but after I keep adding more chlorine, now it's going to NCl3, which will readily go to N2 gas. It's leaving the system. There is no oxidizing agent or the combined chlorine is now decreasing, right. So that's what we see, destruction of chloramines and chloroorganic compounds. They transform to nitrogen gas and go. So that is why even though I keep adding chlorine, the residual chlorine is now coming down. These combined chlorines also we are considering as residual chlorine. That's why in this phase we see that it increasing until a peak. After I add more chlorine, due to the relevant stoichiometry, you see that it now starts degrading to NCl3 and N2. This is NCl3 and N2 gas, let's see, right. So at this point there is no more H2S or Fe2 plus, no more organics, and all the ammonia has been consumed by this point, and this is called that break point, let's see. So whatever chlorine I add from here will be the free residual chlorine, right. So combined residual, and this is the free residual chlorine, and this I can be sure will be available to kill the pathogens. So what do we have here? Formation of free chlorine and presence of chloroorganic compounds which are not destroyed. So free residual chlorine. So this is break point chlorination. So whenever I add chlorine, I need to add this enough chlorine to take care of all the compounds that can oxidize my chlorine or the oxidizing agent like HOCl, and then I will get that. So that's what we have here, the break point chlorination. So here we have the what do we say, NH4 plus and combined chlorine. Initially most of it is present as NH4 plus, but as I add Cl2, I know that chloramines are being formed, so NH4 plus concentration comes down. But this total, which is NH4 plus chloramines, it's still there. Why? Because during this point NH4 plus is being transformed into NH2Cl. But after a certain point, I know that nitrogen gas will be given out. That's why this total is decreasing, and that's this break point that we saw, just a different profile. So another aspect to note is that if I have wastewater containing ammonia nitrogen or wastewater containing ammonia and organic nitrogen, the profile will be slightly different depending on the organic content. So that's what you see here. You won't see such a sharp break point, but you will see such a tapered one, I guess, right. So that's something to keep in mind. So chlorination break point, we already looked at that. Low point of the chlorine residual is called break point, right. So for example, we saw something like this. Initially everything is consumed, then chloramines are formed, and then the peak comes, N2 is being given out, all the chloramines are going to N2, and this is the minimum, and then whatever I add keeps increasing. That's why it's linear here. All this is the residual chlorine from here. This is the break point here. That's something to keep in mind. And in general, we want it residual chlorine such that it's 0.2 milligrams per liter at the end of the or at the furthermost point on the distribution system. Why? Let's say I'm staying far away and I need to see to it that there is enough chlorine to tackle any microbial growth or any intrusion of sewage or such that can tamper or pollute my distribution network, right. So I need sufficient residual chlorine, and sufficient one is supposed to be 0.2. But if it's greater than 0.5 milligrams per liter, it becomes objectionable, and in India typically we exceed this particular limit. So disinfectant removal. So again, as we mentioned earlier, disinfection byproducts can be formed. So you don't want to have too much chlorine, or even other than formation of disinfection byproducts, too much chlorine is also toxic to us and objectionable. So you can remove chlorine. But how will you remove chlorine? You know that chlorine is an oxidizing agent. It's an electron acceptor. So you can add any other benign electron donor, let's see, or reducing agent. Chlorine is an oxidant, so it can readily react with SO2. So if I add SO2 to HOCl, so SO2 right? A reducing agent will be oxidized to SO4 2 minus. HOCl, which is an oxidizing agent, right, will be reduced to Cl minus. You can check the oxidation states of sulfur and oxidation states of Cl, let's see, and then you will understand which one's increasing and such. But as you can clearly, sulfur is being oxidized, right, and Cl is being reduced. So that's what you can do. And SO2 again with NH2Cl or combined type of chlorine, again different kinds of reactions, let's say. Or SO2 in water can form sulfurous acid, right, not sulfuric acid, and sometimes we can add this itself directly, sulfite, a strong reducing agent. It can be added as Na2SO3, sodium sulfite, let's say. All these are reducing agents. Why are we adding them? To take care of the high or possibly high oxidizing agent concentration. That is why we looked at electron transfer or briefly looked at the redox reaction related aspects, right. So, ozone disinfection. Until now we were looking at Cl2 or combined forms of what do we say, chlorine and so on and so forth. Now, let us look at ozone. It is the most or one of the most, or I think second most strongest oxidizing agent available. The strongest one is the hydroxyl radical, that is also formed in or during ozonation of water. Ozone is a gas, it can be produced in situ. With corona discharge, you have ozone generators. As we mentioned, it is much more powerful than HOCl. It will directly oxidize the cell wall of the microbes, similar to the action of your particular chlorine or the chlorine based oxidizing agents. Depending on the pH, it can also form another strong oxidizing agent, which is OH minus. And the half reaction, where we see that it is an electron acceptor, is this. It can also lead to increase in concentration of O2. So, that is one reason why I like addition of ozone, right, addition of ozone. Why is that? When I add ozone, the dissolved solids, total dissolved solids in the water are not increasing. But if I add Cl2 or such, we see that we are adding Cl minus to the solution. So, we are adding the total dissolved solids, which is never good in general. So, here with ozone, though, we are adding oxygen to the water, and also ozone we know is a very strong oxidizing agent. It will also be able to degrade the residual organic content pretty well, and disinfection byproducts are pretty less or non-existent, especially if there is no Br minus. If there is Br minus, it can react with ozone to form some disinfection byproducts, but that is typically not an issue. Again, as I mentioned, it depends on Br minus concentration. So, this is dissolved, I guess, right. So, let us move on. So, how do I understand that it is a strong oxidizing agent compared to OCl minus? We look at Pe naught. So, Pe naught is at the standard conditions minus log activity of this hypothetical electron. So, it is logarithmic based. So, 28 and 35. So, 10 power 7 times, I guess, right. So, 35 minus 28 is 7, but Pe is log. So, you understand how strong the oxidizing agent is or ozone is compared to OCl minus. Let me move on. So, advantages in general does not form harmful DBPs, very effective against taste and odor causing compounds, and because of its fast kinetics and relatively high oxidation potential, you are going to have less contact time, but does not create disinfecting residual. Why? Because it is so fast acting, the kinetics are so fast of this particular oxidant that it does not stay in water for long. So, if I ozonate it now, I think 30 minutes later you are done with most of the ozone will be degraded, let us say, but that is not the case with chlorine. So, you can have ozonation to take care of your residual organics and pathogens, and add some chlorine so that you can have your what is this residual chlorine, let us see. And obviously, it needs a more capital intensive setup, thus it is more costly than chlorine disinfection. So, UV, the last one, which is not a chemical based, UV. So, we have visible light here, light, right. You can see my face because they have the light set up here. UV, you can't see that ultraviolet radiation, yes. So, here the disinfection is caused by directly damaging the nucleoids, let us say, or nucleic acids. I think I have picture later. Depending on the mode of operation, it can form hydroxyl radicals, but we are not concerned about it now. especially when you have UV and in water, and add H2O2 to water, you will form this very strong hydroxyl, very strong oxidizing agent, which is this hydroxyl radical. So, the radiation is produced by UV lamps, and there are different kinds of lamps, low pressure, though I guess it's a misnomer to say it's low pressure, but the primary aspect of low pressure or UVL, low pressure, is that they emit light, not light, radiation only at one wavelength. This is 254 nanometers, or to be specific 253.7 nanometers. It is of great relevance because at this particular UV wavelength pardon me, most of the DNA and RNA of concern will absorb the UV or the radiation, and if they can absorb it at that particular wavelength, obviously the energy is going to be transferred and you will have damage of the RNA or DNA and thus inactivation of the relevant pathogens. With respect to medium pressure lamps, it is not as if they do not emit UV monochromatically. This is monochromatic UV, monochromatic radiation. Here they give it out at a range of wavelengths. But what are the issues? Here interferences, not inferences, interferences due to absorption of radiation by other dissolved substances. For example, here is my UV lamp, right, say submerged, and the water is flowing around it, and this is my cell, and the cell has to absorb, or the UV has to penetrate that particular cell, or the UV radiation or photon has to reach that cell. But if I have suspended solids or other compounds which absorb the UV, meaning other interferences, then obviously the effectiveness is going to be limited. So, I might then need to have higher intensity. That is what we are saying. So, just let us look at this. So, what do we have here? 100 to 400 nanometers, around this I guess, or 500 to or beyond 600 nanometers, it is visible I guess. But what is this range? Let us look at that. Between 100 to 200, UV is absorbed by water itself, and between 300 to 400, region where neither DNA nor water absorb UV. But there is a sweet spot between 200 to 300 where which we call as the germicidal range, where the DNA and RNA absorb UV, let us see, right, and that leads to damage of the RNA or DNA, and that will affect the replication of the relevant pathogen. So, UV, as I mentioned, monochromatic, low pressure lamp, UVL, it will emit light or not light, radiation only at 254 nanometers, that is what we see here. But UV medium pressure, it will emit radiation over a range. It will be effective if we have pathogens that absorb light at radiation, I should not say light, radiation at different wavelengths, and ineffective if they do not absorb radiation at the different wavelengths. So, that is something to keep in mind, let us see, right. So, here is one graph that was presented by my advisor during my time. So, here we see that at 254 nanometers, DNA absorption is pretty good, let us see, right. So, ratio of lambda by 2 lambda at 254 nanometers, and here we see the wavelength, let us see, right, comparing the spectra for parvum and coliphage with absorption spectrum for DNA, let us see, right. So, you can see that it is pretty good. At 254 you see the peak, right, and that is why 254 is remarkably effective at killing or not killing, inactivating pathogens. So, that is why you would see many people trying to sell UV boxes or UV radiation chambers for, let us say, as corona killer blah blah and such. But again, if I have a paper and I put it in a UV chamber, okay, the top surface, bottom surface not really, and again contact time is an issue. So, these UV based radiation chambers for killing corona, especially corona virus on surfaces, I would say all these are mostly trash or short term stars, let us say, right. So, again it is with respect to how effectively the UV can penetrate or be accessible or be absorbed by the coronavirus. If it can't kill the virus, let us see, right. And how is it that it works, UV? So, UV, as we know, can be absorbed by DNA or RNA. So microbes. So viruses, let's say, talk about viruses, can have DNA or RNA, let's say. DNA looks like will help or will tell you how the structure will develop, and RNA will dictate how the metabolic process go through or take place. So in DNA, as we mentioned earlier, we have different nucleic acids. So there are 4 nucleotides of concern: adenine, guanine, thymine, and cytosine, I guess. Hopefully my pronunciation is not too far off from the correct pronunciation. So A, G, T and C, let's say. And this UV will be absorbed by this thymine, yes, and after UV radiation, dimerization will occur, right? Thymine dimerization. So why is this relevant? Let's say because with normal DNA, this is how replication will take place. DNA replicating, as in the cell is replicating, the microorganism or pathogen is replicating, it's growing. If it doesn't grow, it will die soon. The lifetimes are pretty short, obviously, right? So here though, with respect to this change in the DNA, the replication stops at that particular dimerization. So that's how I guess you are going to have what do we say, UV inactivating microbes. And sometimes people talk about, okay, it does not kill, it does not disrupt the cell wall. Well, you see, pathogen does not survive out there for a long time, at least in water and such, right? So in general, replication is what we want to stop if we do that effectively, especially if we do that effectively. So as you see, the UV radiation is pretty good way to go about it. But again, even with respect to other disinfecting agents and such, different viruses, they can repair themselves, and that will also be the case with respect to some repairing whenever they are affected by UV radiation. But let's not go there, let's see. So disinfection kinetics, it's modified Chick-Watson's law. Again, we have a rate, we have another rate constant. Instead of concentration, we have intensity, right? Effective germicidal intensity. How intense is it? Let's say, for example, if I take a intensity meter and go out there in the sun in the afternoon, the intensity is very high, the reading is high. In the night, intensity is less, right? How much, what do we say, energy per unit area per time? That's what it's going to give me an idea about. What is energy per time? Joule per second per area, let's say. And microbial concentration. I plug it into the reaction or equation for plug flow. This is what I get. And I, right, which is nothing but, what is it, energy per time, right, per area, right? Energy meaning, we know that hc by lambda for a photon with lambda wavelength. So that's how we can get it. So if I multiply that by theta or the time, so I'll get energy I into theta will be energy per area, which is called the dose. That is what we have, UV dose, 140 millijoules per centimeter square. So all those people who sell random UV lamps, so you need to be concerned about what is the intensity, how much is the contact time it will achieve, and is there uniform, what do we say, distribution of that UV intensity. Without that, the relevant chamber is just junk. So how does it work? Typically we have the submerged UV lamps, and I think we saw this even in the case of the IIT Roorkee SBR plant, where we had a submerged system. So this is what it looks like. There is a quartz sleeve. Why quartz? Because glass will absorb UV, so UV won't pass through. And if you don't have the sleeve, water will come in contact with the lamp, and obviously you are going to have short circuiting. So you will have a quartz sleeve. Within that you will have the UV, and UV will come out and obviously will penetrate the quartz or pass through the quartz sleeve, and then you are going to have irradiation of the water. Again, because the kinetics is so fast, especially intensity, you can maintain it pretty well. You are going to have what do we say, just small chambers being good enough to cause your relevant disinfection, especially with UV. Obviously scaling and such, you have to look at it, but that's a different aspect. Operation characteristics, obviously UV, if there is a light, there is disinfection. No UV, no disinfection. So there is no chance of residual, so that's one aspect. Turbidity has to be low, otherwise due to interferences, the other compound suspended solids will absorb the UV. Simple operation, but I need to clean the surfaces that come in contact with wastewater to minimize biofilms that can again absorb UV, let's see. So, we have one question and I will end today's session and disinfection and wastewater with this session. What is the pH of a water at 25 degrees centigrade that contains 0.5 milligrams per liter of hypochlorous acid? Okay. So, the question is not very well framed, but we will frame it better later on. So, there is what is the pH of a water that contains 0.5 milligram per liter of HOCl at equilibrium. Assume equilibrium has been reached. So, this is the key. It is not as if it is being added initially, I guess. So, neglect dissociation of water, not a great aspect, but fine, and report the answer to 2 decimal places. Okay. First thing is I have this, which is HOCl concentration, right, and I am going to have to look at it, right. Again, this is not a well framed question, but we will try to make do with what we have. Also, if the pH of solution was increased or decreased to 2 to 7, what would be the OCl minus concentration in milligram per liter? So, let us see what the approach is. First, what are the equations that we want or such? Before that, we want pH equal to minus log concentration of H plus. So, one unknown is H plus, and HOCl will be in equilibrium with OCl minus and H plus, let us see, right. So, this is a potential unknown, one unknown, 3 unknowns, but pH is what we are trying to find and HOCl is what we already have. So, we need a way to be able to get or what do we say, calculate OCl minus. So, in effect we have 2 unknowns, let us see, right. In effect we have 2 unknowns because HOCl is known. So, I need to have 2 equations to be able to solve for this. Certainly, one equation is that Ka is equal to what now? I know that Ka equation is equal to activity or concentration of H plus into concentration of OCl minus by concentration of HOCl, right. So, this is one equation. So, here you see the issue with why I say the question was not very well framed, but assuming that water is not dissociating, which is not a great way. Water not dissociating meaning water will always dissociate into H plus and OH minus, but here they are asking us to assume that this does not happen. So, that is not a great aspect, but why is it that they are asking us to assume that? Because then you can say that whatever HOCl has dissociated will either be as OCl minus as H plus, meaning OCl minus concentration will then be equal to H plus, but that is not the usual case. Why? H plus can react with OH minus to go to H2O, but that is what they said, do not look at that. So, in effect our 2 unknowns become 1 unknown, and with just this one equation we can solve for this unknown, right. So, that is something to keep in mind. So, what do we have? We have that know that Ka is equal to, but we just saw that if it is at equilibrium and if water dissociation is not considered, OCl minus and H plus concentration will be the same, let us say. So, assuming that this will transform into H plus square by HOCl, and I know HOCl concentration, I know Ka or pKa is 7.5. So, Ka is 10 power minus 7.5. So, from that I can calculate my H plus. Let us see what we have. So, HOCl milligrams to moles per liter. So, what do we have? I think how much are we adding? HOCl is 0.50 milligram per liter. So, I am not sure why my student took it as 50 milligram per liter. So, we can consider that to be a typo either in the question or here. So, let us just say it is 50 milligrams of HOCl per liter of water. I want to convert this into moles because all these equations, let us say in the equilibrium constant, this equation all the units are in moles per liter, let us say, or molar units, let us say. In general it is supposed to be molal, but for now we will consider molar units. So, how do I do this? I need to get the molecular weight, let us say, right. So, if I have that, I will have grams of HOCl per 1 mole of HOCl. So, grams of HOCl cancel out and I will get it. What is the molecular weight? So, looks like it is 52.45, H is 1, O is 16 and Cl minus is 35.45. So 17, 7 plus 5, I guess, yes, 52.45, let's say, right? 17 plus 15, fine, 52.45. So that's 52.45 grams of HOCl per mole. So they cancel out, and the units, you can look at it if there was an error made here. It looks like I see that I get it in terms of 9.53 into 10 power minus 6 moles, I guess. Because of the way it was calculated, I am not sure if okay, milligram per gram, so it should probably be moles. Again, we are looking at the approach, not the actual answer. Then we move on. We know that this is the equation, and Ka is equal to this, pKa equal to 7.54, it seems. So from that, Ka is equal to 10 to the power of minus 7.54, meaning Ka equal to this. You can plug this into the calculator, and HOCl, we just calculated that to be 9.53 into 10 power 6 molar or moles per liter. So at equilibrium, assuming water dissociation does not take place, this is the case. But again, in the questions that I ask, I am not going to do this. So from that, I can plug it into that equation that I wrote down earlier, and I seem to get a pH of 6.28. Again, this is the approach, but if there are any calculation errors, you can look at that. And then, people ask if the pH is increased to 7, what will be the OCl minus concentration. So the approach here should be, let's say, I know the equilibrium concentration of HOCl to be 9.53 into 10 power minus 6. I know that OCl minus concentration will be equal to the H plus concentration from here, that is equal to 5.24 into 10 power minus 7. So the total OCl or OCl total, which is equal to HOCl plus OCl minus, will always be constant, because we have this graph, if you remember. This is HOCl, this is OCl minus, HOCl, OCl minus. So you see the maximum here, let's say this is it. So if I, at any point, the total will be the same, this plus this. So if the pH is 3, or if the pH is, let's say, 11 or 10, the total will always be the same, OCl total will be the same. So using that, I can calculate it. Why I need two equations now? Because if I change the pH, which was at 6.28, and take it to pH of 7, what is happening? We have this graph, right? Let's have this. I know that the pKa is 7.5, right? So earlier it was at 6.2, right? 6.2. So if I increase it to 7, I am going out here, let's see. Let me try to draw that in a better manner here. So this is my HOCl, which is decreasing with increase in pH, and the other one is my OCl minus, and this point is 7.5. And earlier I got my pH to be 6.28. So at 6.28, let's say that this is the case. At 6.2, let's say this is 6.2, this is the case, right? But if I increase that to pH of 7, obviously this will be the case. But one aspect to note is that the total of HOCl and OCl minus will be the same. So that is the key to get the second equation. OCl total is HOCl plus OCl minus, and we already have another equation for Ka. So I have two unknowns, which are HOCl and OCl minus. These are my two unknowns. Because pH is 7, H plus is already known. So I have two unknowns, two equations. What are the two equations? One is this equation, and the other one is the Ka equation, right? So I have two unknowns, and I have two equations. I can solve that. That is the way to go about it. But people typically make blunders. Let's see if my TA was able to get it right or wrong. So he says Ka is equal to H plus OCl minus by HOCl, fine. H plus is 10 power minus 7, fine, that is a known value. Ka is already known, so that is also fine, we have that. So okay, now we see that OCl minus, and he is substituting this H plus and such into this, which is also fine. But again, as is the case, and how this is how people make errors. So he took the HOCl concentration from part A to be the same as here, but you should know better. As you saw here, the HOCl concentration at 6.2 was this, but after increasing the pH it will decrease. So, the HOCl concentration is not the same. So, the approach should have been this. So, this is a common mistake that people make. So, I wanted to use the issue at hand to be able to illustrate this. So, I guess with that we are done with disinfection. So, we are done with wastewater. So, from the next session we will start looking at water treatment and how to go about it. Again, what is the principle? Well, I think we looked at this pretty well. So, thanking you for your patience, I will end today's session.